Neuroplasticity is the brain's extraordinary capacity to reorganize itself by forming new neural connections throughout life. This concept challenges the traditional view that the brain's structure is fixed in adulthood and underscores the dynamic nature of the brain. In this comprehensive explanation, we will delve into the mechanisms, types, significance, and applications of neuroplasticity, shedding light on its profound implications for learning, memory, rehabilitation, and mental health. Mechanisms of neuroplasticity. Synaptic plasticity. At the core of neuroplasticity is synaptic plasticity, which refers to the ability of synapses, junctions between neurons, to strengthen or weaken over time in response to activity. Long-term potentiation, LTP, and long-term depression, LTD, are two fundamental processes involved in synaptic plasticity. LTP strengthens synapses by increasing the efficiency of signal transmission, while LTD weakens synapses, promoting pruning and refinement of neural connections. Structural plasticity. Structural plasticity involves physical changes in the brain's structure, including the growth of new dendritic spines, the formation of new synapses, and the sprouting of axon terminals. This process enables the brain to adapt to new experiences, learn new skills, and recover from injuries. Neurogenesis. Neurogenesis is the generation of new neurons, primarily occurring in specific brain regions such as the hippocampus and the olfactory bulb. While once controversial, it is now widely accepted that neurogenesis persists into adulthood, offering opportunities for brain repair and cognitive enhancement. Types of neuroplasticity. Experience-dependent plasticity. Experience-dependent plasticity occurs in response to specific experiences or learning tasks. For example, musicians exhibit structural changes in brain regions associated with motor skills and auditory processing, reflecting the refinement of neural circuits through musical practice. Developmental plasticity. Developmental plasticity refers to changes in the brain's structure and function during critical periods of development. It enables the brain to adapt to its environment and is crucial for processes such as language acquisition and sensory integration. Homeostatic plasticity. Homeostatic plasticity maintains the stability of neural activity within a functional range by adjusting synaptic strength in response to changes in activity levels. This ensures that neural networks remain responsive to incoming stimuli while preventing hyperexcitability or synaptic saturation. Significance of neuroplasticity. Learning and memory. Neuroplasticity underlies the brain's ability to learn and form memories. Through repeated stimulation and practice, synaptic connections are strengthened, encoding information and skills into long-term memory. This process is fundamental to education, skill acquisition, and cognitive development. Recovery from brain injury. Following injury or trauma, the brain can undergo remarkable recovery through neuroplastic mechanisms. Adjacent regions can assume functions of damaged areas, and new connections may form to bypass injured pathways. Rehabilitation strategies harness these mechanisms to promote recovery in conditions such as stroke, traumatic brain injury, and neurodegenerative diseases. Adaptation to environmental changes. Neuroplasticity enables organisms to adapt to changes in their environment, whether physical, social, or cognitive. This adaptability is crucial for survival and allows individuals to learn new skills, adjust to new situations, and cope with challenges throughout life. Mental health and well-being. Dysregulation of neuroplasticity has been implicated in various psychiatric disorders, including depression, anxiety, and addiction. Understanding how neuroplasticity is altered in these conditions offers insights into potential therapeutic interventions, such as cognitive behavioral therapy, mindfulness practices, and pharmacological treatments. Applications of neuroplasticity. Brain training and cognitive enhancement. Brain training programs leverage neuroplasticity to improve cognitive functions such as attention, memory, and problem-solving skills. These programs often involve engaging tasks designed to challenge and stimulate specific brain networks, promoting synaptic strengthening and cognitive improvement. Neural interface technologies. Advances in neural interface technologies, such as brain-computer interfaces, BCIs, capitalize on neuroplasticity to restore lost sensory or motor functions. By establishing direct communication between the brain and external devices, these technologies can bypass damaged neural pathways and enable individuals with disabilities to control prosthetic limbs or interact with computers using their thoughts. Therapeutic interventions. Neuroplasticity-based therapies are increasingly used to treat neurological and psychiatric disorders. Techniques such as transcranial magnetic stimulation, TMS, transcranial direct current stimulation, TCS, and deep brain stimulation, DBS, modulate neural activity to alleviate symptoms and promote recovery in conditions such as depression, Parkinson's disease, and chronic pain. Conclusion: neuroplasticity is a fundamental property of the brain that underlies learning, adaptation, and recovery. By understanding the mechanisms and types of neuroplasticity, researchers and clinicians can develop innovative strategies to enhance cognitive function, facilitate rehabilitation, and improve mental health outcomes. Embracing the plasticity of the brain opens new frontiers for education, medicine, and technology, promising a future where the brain's potential for change is fully realized.